So we'll go ahead and get started here this morning. And I'd like to be kind of spending most of our time kind of really today and really probably a lot of the rest of this week focusing on, we're going to be pretty much focusing on covalent bonding, looking at how do we actually go about drawing Lewis structures, which things probably some of you may have seen yesterday in lab a decent bit. If you haven't been to lab yet this week, you'll probably see there too. So today we're going to focus most on kind of drawing Lewis structures, a lot of kind of the finer details that can go into these. The good news, it is still very systematic. It's going to follow the same set of steps every single time. But there are a couple little things you kind of want to look out for as we're going through that I'll kind of point out, particularly as we get into things with, again, formal charge, the idea of resonance that we'll talk about more today, and then looking at some of the exceptions for kind of general octet. And from there, I don't know if we'll end up having time today, but at least by Thursday, I'll probably get into some of the VSEPR things you'll see in lab as well, the shapes of molecules. All of that, though, is going to be tied kind of to Lewis structures. So really a lot of what we're kind of starting now with these Lewis dot structures, it's kind of one of the more important things, I think, out of 1211, because it's going to, one, for almost any chemistry you take, probably always going to be around to some degree. And two, it gives us so much information. There's things like the start of 1212 is going to focus a lot on something called intermolecular forces. But to figure those out, we have to know if a molecule is polar or not. But to figure that out, we need to know what kind of the molecule shape looks like, which means we need the Lewis structure. And so there's like a lot of pieces kind of all interwoven together. This is kind of the start of a lot of that. So what I want to do then first is kind of just go through the process of reviewing kind of drawing Lewis structures that we had kind of left off with last week. So looking at just kind of a couple quick examples of kind of our general steps. And then we'll get back into looking at kind of some new things with resonance and some other finer pieces with some of our exceptions. And so for these first couple examples, I'm also going to show kind of using active, like how active works for drawing some of these. So if you're looking at any kind of homework problems or things on there, what that tool looks like. So this first one wants us to draw a Lewis structure of NF3. And if I go into this kind of drawing tool, this is what the active tool is going to look like for drawing our Lewis structures. So in terms of starting this, what are my normal starting steps for drawing Lewis structures? What are kind of the first couple things I'm always looking to do? One thing I'm always going to want is to find how many valence electrons I basically have to work with. Should be one of the, kind of the first things we're usually trying to figure out. How would I figure that out for NF3 in terms of finding my valence electrons? How many does nitrogen have? And how are we figuring that out? If we're looking, I see everyone kind of looking over at the periodic table. How are we counting that? Yeah, it should be 5. And remember, we're really just kind of counting our way across. Column 1, and I can actually kind of pull up the periodic table view here. Like column 1, everything here, 1 valence electron. Column 2 is 2. We're skipping kind of all of this middle D block, although really the group numbers that these things have are also the number of valence electrons those elements would have. But in the case, if we're skipping the D block, boron on down, it's number 13, but all of those have 3 valence electrons. Like carbon on down, 14 is going to have 4 valence electrons. Nitrogen down is going to be 5 in this case. If we work our way over to fluorine, everything in the halogen is going to have 7. So in terms of kind of what we're starting with, and I think I'm just going to put nitrogen there for now. NF3, nitrogen's got 5. Each fluorine is going to have 7. So 7 times 3 is 21, plus 5 is 26 electrons. Is going to be that total. So I want to kind of keep that in mind kind of as we're going through this. The other starting piece is putting together a skeletal structure, right? So usually that means picking a central atom. How do I know what the central atom of most of these structures are going to be? Based on like the formula, if we're given the formula. You'll usually see the descriptions as you try to put the least electronegative element as the central atom. But if I'm looking at a chemical formula, usually the least electronegative one is just the first one most of the time. And really, if it's not the first element, probably we're going to tell you what the central atom is. So in this case, like nitrogen being the first element that's listed here, means that it's going to be our central atom. And so this nitrogen here that I have kind of highlighted, I've clicked on, if I click on something else, you notice it'll turn red kind of in this little building module. But if I click on the nitrogen over on the right-hand side, I can put up to 3 bonds. That just means I have 3 things now like attached to that nitrogen, right? Because I have 3 fluorines that I want to attach to it. So I'm effectively just drawing single bonds to all 3 of the fluorines. And this is my now skeletal structure that I'm going to start with. So once I've kind of organized my central atom, I have all of my other things kind of attached to single bonds, what's my next step kind of in our process? Usually that's going to be filling octets, but where do I start? I have to start on the outer atoms first. So outer atoms, we're going to fill octets. So how I would do that if I'm looking at like a fluorine on the outside, remember a bond already has 2 electrons in it. So that fluorine already has 2 electrons. To get to 8, it needs 6 more. So those 6, as I add them, you see like a kind of scroll feature and active that can do that for us. Adding those 6 electrons, it automatically groups them kind of as 3 lone pairs. And I need to do that for each of the outer atoms. So if I do that for each fluorine, here I can add all the lone pairs. I can also add all the lone pairs. Now what I want to do is look at, once I've filled all the outer octets, I want to count how many electrons have I used to get to that point. So if I'm counting all of my electrons that are currently in that structure, how many have I used up to this point? And if you're looking for kind of a quick way to usually do that, if all of my outer atoms have an octet, I have 3 outer atoms. If they have 8 electrons each, 3 times 8 is 24. Should be how many electrons I currently have up here. So I have 24, but when we counted all of our valence electrons at the start, we had 26, right? So the reason I counted those at the start is now I want to see how many are left, right? So 26 minus the 24 I've used means I still have 2 electrons to put in the structure. If I have leftover electrons, where do they go? Yeah, always the central atom, and they're always going to go on that central atom as a lone pair. So that nitrogen ends up with a pair of electrons on it. Now, one thing active does, and we'll get into more of this probably on Thursday, as you kind of adjust what's on that central atom, active kind of automatically configures it into the rough 3-dimensional shape that that thing's going to look like. For right now, for just drawing the Lewis structures, don't necessarily worry about that. That's not the important feature. We'll get into talking about the shapes a lot more on Thursday, I think. For right now, our main focus is just getting the Lewis structures themselves, like getting comfortable kind of drawing these Lewis dot structures. All right, so other pieces then from here. Once I've added all the electrons that we have, we're usually going to check, does the central atom have an octet? So if I look here, does the central atom have an octet right now? Yes, it's got 3 bonds and 1 lone pair. So like in terms of counting, like this bond is 2 electrons. There's 2 more is 4, 2 more is 6, 2 more from the lone pair is 8. So the nitrogen has 8 electrons around it. So it's happy to have that octet. So I don't have to do anything as far as like making multiple bonds or anything like that. The only last thing to usually look for is formal charge. So as kind of a review, how do we calculate formal charge for an atom in a structure? Remember that from last week? Formal charge for any one atom is usually going to be the number of valence electrons that atom has on its own, minus the number of electrons it has in lone pairs, minus the number of bonds it has. So for instance, if I'm looking, say, at like this fluorine, like that fluorine has 7 valence electrons normally. It's got 6 electrons around it that are in lone pairs, and it's got 1 bond. So 7 minus 6 minus 1 is 0. And active does have actually kind of a nice feature here. This little formal charge button, if you click it, pops up the actual formal charge of all the atoms in that structure that you've drawn. So it'd be kind of a nice way to kind of check formal charges as you're kind of using that to do some of these examples too. But remember, our goal for formal charges, we do want as many 0 formal charges as possible. And the nice thing is it is very pattern heavy. And kind of the more examples you do, the quicker it is to find formal charge, in the sense that like if we have a halogen, like any halogen, like fluorine in particular, typically wants 3 lone pairs and 1 bond, because that's what's going to give it a 0 formal charge. So our other fluorines that are here, they all have 1 bond and 3 lone pairs. That means all of them should have 0 formal charge. Right? It's very kind of pattern heavy kind of in that way. The nitrogen that we're looking at here in the middle, nitrogen has 5 valence electrons normally that it started with. It's got 2 in a lone pair and 3 bonds. So 5 minus 2 minus 3 is also 0. And so what we'll see for nitrogen, nitrogen usually likes to make 3 bonds and have 1 lone pair. That's kind of its normal structural pattern that gets a 0 formal charge. And so when nitrogen does something that's not that, then we know that we have kind of formal charges somewhere, or that maybe our structure is not what we're, not the best version of it yet. All right, but since everything has 0 formal charge, the central atom has an octet. That basically means this is our best Lewis structure that we can draw for this molecule. Now, the last thing we're going to talk about, not quite just yet, is resonance. If there's no multiple bonds in the structure, we don't have to worry about resonance yet. So in this case, there's not going to be any resonance in this particular example. That's usually the other thing we check for, along with kind of formal charge, is kind of like a last check to make sure we're not missing anything in the structure. All right. Questions kind of reviewing those steps. For Oh, for the different counting. So for the fluorine, if I'm going through like doing the formal charge, like it has 7 valence electrons normally from where it is in the periodic table. We have 6 total electrons in lone pairs. I know it's going to be high to 0 here, but it's got 6 dots for basically the 6 electrons in lone pairs that are around it, and then 1 bond. So it'd be like 7 minus 6 minus 1. We're basically taking like its normal valence electrons minus all of these electrons from the lone pairs minus the number of bonds that it's making for finding the formal charge. 7 minus 6, yeah, minus 1 will give us 0. That's the formal charge of this machine. So when we're first putting the structure together, and kind of probably the general rule of thumb is like once you make your skeletal structure of things, you have like a single bond from your central atom to the outer ones. We're always going to fill the outer octets. Well, there's 2 electrons in this bond. That means we're pretty much always starting by adding 3 lone pairs to things. And then it's just a matter of, do we need to make any multiple bonds to satisfy octets of like central atoms or other things. So we added all of these electrons to each fluorine because we want all the outer atoms to always have an octet of electrons or 8 electrons. And so if we get 2 from this bond, then we have 6 more that we have to add to these lone pairs to get to a total of 8 for that outer atom. Right. So and I think the more of these we do, I think some of those patterns will come up a little bit easier. So let's take a look at one more. And this will take one that has multiple bonds, and then we'll start getting into some stuff with resonance. All right, so this one wants us to draw the Lewis structure of N2. So a little bit different. It's a smaller molecule, only 2 atoms. Both of our atoms in this case are going to be just nitrogen. So skeletal structure, I'm going to start with just basically single bond connecting the 2 of them. But we do want to know how many valence electrons we're going to be working with. So how many total valence electrons should N2 have? Yeah, it should be just 10. We said earlier, nitrogen's got 5. So if I have 2 nitrogens, 5 times 2 is going to give us 10. Now, for our steps, normally we just pick, central atom and look at our outer atoms and fill kind of the outer octets. In this case, there's not a clear central atom, but you can kind of just pick. Like anytime you only have 2 atoms, if you're drawing its Lewis structure, kind of doing your steps, you can just pick one to be the central atom and then the other one to be what we consider kind of the terminal or outer one. So let's say I pick the left one as the central atom. That means I want to fill my outer octets, which means I'm going to fill the octet on the other nitrogen. So filling the octet on this nitrogen, I have 2 electrons already from the bond. So basically I have to add, again, kind of similar to the last example, adding 3 lone pairs to that nitrogen is going to get it up to 8. And then once I've done that, that's kind of the only outer atom, the way we're looking at this one. So if I started with 10 electrons, currently in the structure I put in 8. That means I have 2 electrons left. So now I go back to my central atom. So that'll be this nitrogen. And I'm going to be adding those last 2 electrons that I hadn't added yet. But if I'm looking at that central atom, is everything happy with the number of electrons it currently has? How many electrons does that left nitrogen have right now? Yeah, it's only got 4, but it needs 8. Right? It wants 8. So the way how am I going to go about getting that to 8 electrons then? What do I have to do? When the central atom doesn't have an octet yet, this is when we're going to be making multiple bonds, right? And the way that we make multiple bonds is we're going to take a lone pair off of the outer atom, and we're effectively going to move that lone pair to the actual bond. So in this case, like if I take, it's like come to this nitrogen and take 2 electrons off, I'm basically going to add a bond between those nitrogens. I'm moving where those 2 electrons are. So I'm not changing the total number of electrons that are anywhere in my structure. I'm just kind of moving them or relocating them. But doing that just once isn't really enough yet, right? Because this left nitrogen still only has 6 electrons. So I actually need to do that one more time so that I can take 2 more electrons off the right nitrogen to make now a triple bond between those 2 nitrogens. And now if I'm looking at now both nitrogens do have an octet. Took a triple bond to do it. But if I think about patterns, this still kind of makes a little bit of sense, right? Because nitrogen, we said a minute ago, for formal charge, nitrogen likes 3 bonds and 1 lone pair. Well, those 3 bonds, they could be 3 single bonds, or in this case, it could be a triple bond. It doesn't really matter what the combination of the bonds is. It wants to make 3 bonds, have 1 lone pair. That's kind of its preferred configuration to have that 0 formal charge. And so this ends up being our Lewis structure for N2. Questions kind of going through that, thinking about going through those steps? Yes.
So the reason that made our central.
Yeah, it didn't have an octet yet. So we're making multiple bonds, basically as many multiple bonds we need you to get up to an octet. And in fact, as we talk slightly more about octet exceptions with expanded octets here in a little bit, we'll see that sometimes if something can expand an octet to get rid of formal charge, we'll actually do that also. We'll see that kind of in a couple examples today. All right, so next piece then. I want to talk a little bit about resonance and what resonance is. So I'm going to do this example NO3 minus, although I'm going to do this kind of the other view as far as drawing this thing. So this will kind of highlight also a couple things. This has got a polyatomic ion. That means we have a charge involved. That means we're definitely going to have formal charges somewhere in our molecule that aren't zero. So we'll want to highlight those, kind of show how all of that usually works. So our example here, we're looking at nitrate, NO3 minus. So going through kind of our normal steps for valence electrons. Nitrogen has, you've seen this in the last couple examples, 5, right? How many does oxygen have? If you look at the periodic table, it's 6, we got 3 of them. And then what about that negative charge? What is that doing here to my total? If it's a negative charge, that means I've added an electron. So that negative charge, we're going to add 1 to our total number of valence electrons. And one other thing you should notice for all of these examples that we're going to have you be drawing structures for, it should always be an even number of electrons. You are not going to see anything that has an odd number of electrons for kind of any of the examples that we actually do. Odd electron species make something called a radical, which we don't talk much about in Gen Chem, but when you get to organic, you kind of talk more about them. And radicals are not very stable. They tend to react with almost everything to try and not be a radical. And so there's things we usually want to kind of avoid, but they do exist. And they're things that'll get talked about and covered a little more, I think, in organic. But for us, kind of in Gen Chem, everything's going to be even numbers. So here, adding up all of our totals, should have 24 electrons, kind of putting all those together. So going through next step, skeletal structure. If nitrogen's first element listed, that's probably our central atom. And really for all intents and purposes, for the examples we see, that first element listed should be the central atom, unless the first element's hydrogen. Hydrogen can never be central, so that would be kind of the one major exception. And if it's anything, if any other time the first atom is not the central one, we're probably going to tell you what the central atom is. I don't think there's many for Gen Chem that would ever come up for. But in our case, we're going to draw a nitrogen with all 3 oxygens attached to it. Next step then, after we have our skeletal structure, we have our total number of electrons. We're going to add the outer octets. So again, the outer oxygens, each one currently has 2 electrons from just that one bond. So really filling the outer octets, it's basically always just adding 3 lone pairs to each of them to start. It's kind of always the starting step, because that's what's going to get our octets on those outer atoms. So add 3 lone pairs to each one of those oxygens, gives each one of those an octet. And now how many electrons have I used to get to that point? If I have 3 outer atoms that each have 8 electrons each, that's 24. I started with 24, so that means I have no more electrons to add to this. Does that mean this is my final structure? What's still wrong with this structure at the moment? Yeah, the central nitrogen still needs 2 more electrons, right? So the way I do that, I have to make a multiple bond, but here I have options, right? The last example, there was only 1 outer atom to take those electrons from, but here I have 3 different options of where to take those lone pair of electrons from. So the question is, which one do I take it from? And really the answer is, it doesn't matter. You can do from any of them. So for the first one, anyway, I'm going to take from the top oxygen, and I'm basically just moving those 2 electrons down to make a double bond. Let me make that just maybe slightly cleaner. Now I have an octet for that nitrogen. But really what I have in this molecule, since I could have put that double bond to either of the other oxygens as well, this is what resonance is. So resonance is when you have kind of like equal options of where to put a multiple bond. And there's no difference in terms of like which is better. And when I say that, like there's no formal charge difference, right? Whether I put, and since all of these outer atoms are oxygens, like where that double bond goes really doesn't make a difference. Now, if say one of those outer atoms was oxygen and two of them were like fluorines instead, now I can use formal charge to probably see where that double bond is going to prefer to go. But if all of the outer atoms are equal like this, really that double bond could have gone anywhere. And so the way we often notate this, or the way we show resonance, is we use kind of some double-sided arrows. And a lot of times for these, I won't show the full Lewis structure. I'll just show kind of the double bond moving around to show that the double bond could be in one of these other spots as well. And so that's kind of notation that you'll see for what we call resonance. So resonance is when you have kind of multiple equal ways to draw the structure. And really the other part I want to point out about resonance that's kind of weird, if you have one nitrate molecule or one nitrate polyatomic ion, you are not going to have a double bond and two single bonds. The way that molecule actually exists is that that one double bond, because it could go in any of those three spots, that one double bond kind of almost ends up shared between all three spots. And in reality, every one of those bonds, instead of being just like a plain single bond or a double bond, probably all more like a bond and a third. That one extra bond is kind of evenly distributed between all of them, which is kind of strange, but there's some ways that we actually know that's happening. And so if that double bond could be in any of those spots, it's really kind of almost in all of those spots at the same time to some extent. So two things I want to point out from that. That means every one of these nitrogen oxygen bonds are still equal to each other in terms of kind of like the symmetry or the strength that each of them has. So I'll kind of highlight this here, like all bonds with resonance are equal strength. But kind of the takeaway from that is that they're not really a plain single bond or a double. You do get kind of almost like a bond and a third, or maybe in other examples, like a bond and a half, or you get a bond and 2/3 at times for different molecules. Now, one last thing I'm going to do as far as just the Lewis structure itself, things that have resonance, I do usually want people to show that multiple bond moving around. But also, we're not really done with the full just Lewis structure of my original version of things on the left yet. Anything that has a charge like this, so this thing has a negative charge, and so NO3 minus, anything that has a charge, we typically put that ion in brackets like this with the charge on the outside to show that that's an ion, not a neutral molecule. And the last part of this is formal charge. I still want to indicate formal charges, and anything that is an ion has to have formal charges in it. There's no way around that. And all the formal charges have to add up to whatever that total charge is. Now, sometimes if it's a -1 formal charge, that means there's just one -1 formal charge in the molecule. In this case, there's actually more than that going on. So we probably want to look at each of these and figure out where are the formal charges. Now, the more used to patterns you get, that kind of helps. So for instance, oxygen's normal pattern for formal charge is it likes 2 bonds and 2 lone pairs. That's what gives it a 0 formal charge. And that's what the way I've kind of drawn things here on the left, like this top oxygen has 2 bonds and 2 lone pairs. So that one has a 0 formal charge. And for 0 formal charge, I don't have to indicate anything. But for each of these oxygens on the bottom of that structure, they have 3 lone pairs and 1 bond. So for instance, if I'm doing the formal charge of this oxygen right here, that oxygen normally has 6 valence electrons. It's got 6 electrons in lone pairs, and it's got 1 bond. That's -1. The way we notate that is I'm going to take a negative sign and circle it right next to that oxygen that has that formal charge. And additionally, if I have another oxygen that looks exactly the same, as far as like the number of bonds, the number of lone pairs, it needs to have the same formal charge, right? That bottom right oxygen, that same structure, also has 3 lone pairs, 1 bond. So it should also have a -1 formal charge. Now, the only thing I have to be careful with then, if I have 2 -1 formal charges, but the total charge of our whole ion is only -1, that means I have to have a positive formal charge somewhere also. Well, I've looked at all the outer oxygens so far. Right? The top oxygen is 0, the bottoms were each -1. So what's left now is the nitrogen. And there should hopefully be kind of some bells and whistles going off as we look at the structure, because that nitrogen doesn't follow its normal pattern either. Like nitrogen normally likes to have 3 bonds, 1 lone pair. Here it's got 4 bonds, right? So that nitrogen, 5 valence electrons normally, minus, or they should say 0 first for valence electrons, -4 bonds is a positive one. So nitrogen actually has a positive formal charge in that structure. And so there's our formal charges that are present. Now, sometimes there will be ways to get rid of formal charge like this. In this particular example, there is not. There's just no way for us to do anything to get rid of that. And we'll get into more of that as we talk about exceptions to octet rules here in a moment. So full Lewis structure then for nitrate would basically be everything here that I'm circling. I would want the brackets to show that nitrate's an ion. I want the formal charges there. And then to indicate resonance, you don't need to put all of the other details. I just want to see the multiple bond moving around. Like, because if you put all the details into one, like it's just time consuming to put them into the other. It's not necessarily showing something. But if there is resonance present, I do want to see like what are the other resonance forms. Just show the multiple bond that it can be in those other locations. Okay. Questions going through this example. Resonance, and it's something that as you get to kind of the end of a structure, if you have multiple bonds that you're making and you have multiple spots you could put it, and all those atoms the same, like you have resonance. You have the option to put it in any of those spots. That's what we're kind of trying to show with the resonance, and basically just showing the double bond can be in any of those locations. All right. So the last kind of nuance that I'm going to put into kind of some of these Lewis dot structures is kind of some of the octet rule exceptions that can happen. And so I'm going to talk about these, and then we're just going to go through like a whole bunch of just examples of just drawing Lewis structures. I think kind of putting all of this together. So octet rule exceptions. So there's 2 ways this can go. We can either have what I call an incomplete octet, so less than 8 electrons. And for the most part, this is a shorter list of elements that will do this. The first kind of most obvious one is just going to be hydrogen. Why does hydrogen not want an octet? Talked about this kind of briefly at the end of last week too. Where does our octet kind of like magic number of 8 come from? Why 8? 8's the magic number because that's how many electrons it takes to fill your s and p orbitals. Does hydrogen have a p orbital it even needs to fill if it's only in the first row? No. So hydrogen only ever wants 2 electrons. Right? That's all it ever really wants, which really in terms of our structures, hydrogen is only ever going to make 1 bond. That's pretty much all it's ever going to do. There are some really weird things out there. We can sometimes make it do some other stuff. Nothing we'll ever see in Gen Chem. Like all the basic things hydrogen does, it just makes 1 bond. That's it. That's also why it can never be the central atom, is because it can never make more than 1 bond. Now, the other exceptions for this is going to be group 13 elements. And especially, I'm going to highlight boron. So technically the elements below boron can do this also, but boron is probably the most common one that does this. And boron really prefers 6 electrons. And I'm going to put here like 3 bonds is how it's going to get those 6 electrons. And the reason for that is formal charge. Atoms really want to have 0 formal charge as often as possible in their structures, which means for boron, it actually almost doesn't want an octet because the only way that boron can ever have an octet is to have a negative formal charge. Like if boron has a 0 formal charge, it's basically just going to make 3 bonds because it only has 3 valence electrons. So boron will typically do this because this gives it 0 formal charge. And really, we probably won't see many compounds that contain boron in this class, or really probably a lot of classes like Gen Chem and Organic. But probably the most common ones we're going to see for this, and one that does show up, I think, all the time, is BF3. So let's go through and take a look at what BF3 actually ends up looking like real quick. Question first. Yes, Yeah, all atoms want to have zero formal charge if possible in the structures. Sometimes there's no way around it. They might have to have, like this last example, there was really nothing we could do to the structure to get rid of those formal charges. We will see some other examples that are similar that will have some options to get rid of it here in a minute. But if sometimes they just have to have the negative formal charges based on what's there. All right, so for BF3, if I'm going through kind of normal steps, boron has 3 valence electrons. Each fluorine has 7, as we've seen before. There's 3 of them. So we have 24 electrons again, which pretty much makes this a lot like the nitrate we just did a second ago. And that will have a boron central atom, 3 fluorines attached to it. I can fill all of the outer octets, right? So giving 6 electrons to each of those fluorines gives each of them an octet. And that will use all 24 of the electrons that compound has. The difference here is boron at the middle, if I leave it exactly like it is right now, everything has 0 formal charge. And boron would prefer to keep it that way than to try and make a multiple bond to get to an octet. And there's one other feature of why boron kind of doesn't do this. If I wanted to make a double bond here by moving a pair of electrons, in terms of formal charges, that means that boron is going to have a negative formal charge, right? Because if I did the calculation, like boron's 3 valence electrons minus 4 bonds, right, it's going to be -1. And this fluorine at the top is actually going to end up with a positive formal charge if I do that. Right? Fluorine having 7 valence electrons normally, minus 2 bonds, minus 4 electrons in lone pairs, going to give it a +1. But what's important about this, if I think for a second, what do we know about fluorine and, say, electronegativity? Fluorine is really the most electronegative element on the periodic table, which means when fluorine makes covalent bonds, is the boron likely to pull electrons towards it to get a negative formal charge? Yeah, it's just not going to happen. Fluorine's too electronegative to really have that happen. And so instead, we are going to stay at just a single bond. Boron will not have a full octet, but that is the actual structure then for BF3. There's no multiple bonds that actually end up forming. Boron as a whole, we don't usually see too much probably in general chemistry. Probably BF3, honestly, or maybe other variations where instead of fluorine, it'll use like chlorine or bromine or iodine because it kind of does the same thing. Those are probably the only boron compounds we'll ever see in this class, or even in 1212. And mainly just because boron does a lot of weird things that don't follow kind of normal patterns that we like to talk about in Gen Chem. In fact, boron kind of almost has its own entire unique branch of chemistry that it does that no other element does because it doesn't want an octet when it's kind of making bonds and doing things. And so it kind of just opens up a whole bunch of different things that other elements just don't do. Those are our kind of major exceptions for things that will have incomplete octets. Right? So hydrogen, only ever going to make 1 bond. Boron, technically the elements below it also, although the one that we'll see actually probably do this most commonly is boron itself, where they're only going to make 3 bonds. That'll keep the 0 formal charge, but it means they don't have an octet. Now, the flip side of an incomplete octet for our other exceptions is we can also have an expanded octet. Right? So this means more than 8 electrons. And so there's one major requirement for an element to be able to expand its octet. So in order to have an expanded octet, we need to have access to d orbitals. Right? If we think about kind of, again, 8, that magic number comes from s and p orbitals and filling them entirely. If I need to go over 8, our atom has to have d orbitals as well to be able to put electrons into to go past kind of that 8. So in order to have an expanded octet, the element must have d orbitals. But when do elements start having access to d orbitals? This kind of goes back to quantum numbers. And so if we think like d orbitals, that's an L value of 2. That means that the n value has to be 3 or bigger. in terms of the periodic table, though, that basically just means if N is 3, we need to be in the third row of the periodic table or lower. And in particular, we're never really going to see like sodium or magnesium use d orbitals, but something maybe later on in the third row, like phosphorus or sulfur or chlorine, those have d orbitals, they're just empty, right? Because the 3d, we don't really start filling until after the 4s from kind of some of the electron configuration things we did before. But phosphorus, sulfur, chlorine, they have d orbitals there, technically, for that third energy level. They just don't have any electrons in them. But if we're going to have an expanded octet, that's kind of what we want, is empty d orbitals to put extra electrons into, right? And so that's kind of our requirement. Basically means third row and lower on the periodic table. Any element in the third row or lower does have the ability to expand its octet. So it can have more than 8 electrons around it. And we'll see this in a lot of structures. So for instance, let's take a look at drawing a Lewis structure for SF4. So we can draw a Lewis structure for this, just following kind of our normal steps and patterns. So sulfur, how many valence electrons should sulfur have? It's below oxygen on the periodic table. So like oxygen should have 6. Fluorine we've seen a few times today. Said has 7, we have 4 of them. So 28 and 6 is 34 electrons. Sulfur is listed first, so that should be our central atom. And again, how you orient things here doesn't really matter much right now. I don't care about 3-dimensional shape stuff just yet. Like if we're drawing the Lewis structures, all I care about is the right number of bonds, right number of lone pairs. The exact orientation of how you draw a Lewis structure, I don't care about. We'll have something else to talk about with 3 dimensions on Thursday with Vesper sketches. So going through our steps here, once I have my skeletal structure and total number of electrons, I can fill all those outer octets. So 3 lone pairs on each of those fluorines so that each of them has 8 electrons. And if I've now got 4 octets, 4 times 8 is 32 electrons. I started with 34. That means I have 2 left that have to go on the sulfur specifically as a lone pair. And whether you put it in that corner or if you put it like on the top right or bottom left, doesn't matter. But I have a lone pair of electrons that is going to end up on the sulfur in this. When I go to look at this then at the end, I've added all my electrons. If I look at my central atom to check for an octet, how many electrons does that sulfur have? If it's got 4 bonds, that's 2 electrons each, that's 8, plus the 2 in the lone pair is 10. It's more than 8. So in this case, sulfur has 10 electrons. But as long as the element that's in the middle is in the third row of the periodic table or lower, more than 8 electrons is okay. So more than 8 is okay, as long as the element is in the third row or lower. And so really this actually ends up being our final structure. We can check formal charges, but fluorine in particular, right? We saw that before. Fluorine, or really just halogens, like to have 1 bond and 3 lone pairs. That's a 0 formal charge for them. The sulfur, it's a little bit different than what oxygen normally does, but sulfur has 6 valence electrons. It's got 2 electrons in a lone pair and 4 bonds. It's also going to have a 0 formal charge. So everything here does have a 0 formal charge. That's going to be our best Lewis structure for this. The one thing where this kind of shows up that's a little different, and it shows up a lot for polyatomic ions. If we end up with a structure that has negative formal charges on outer atoms and a positive formal charge on the central atom, if the central atom can expand its octet, it can make multiple bonds to get rid of formal charge. Right? And I'm going to show that here in a second. Like if I look at sulfate in particular, sulfate's going to be a good example of something that can do that. If I go back before, we looked at nitrate up here. Nitrate has negative formal charge on the outside and a positive formal charge in the middle. It kind of is stuck that way. Nitrogen, like if I wanted to get rid of formal charges, I could technically take one of these outer lone pairs and make an extra bond. The problem is nitrogen can't expand its octet, so it can't do that. Nitrogen isn't able to do that, but instead of nitrogen, if that was like phosphorus, it would. And so there is a little bit of a difference between kind of the second row elements and some of the rest of the periodic table in terms of a couple of the patterns that we see. Like oxygen pretty much always will be 2 bonds and 2 lone pairs. Sulfur's in the same column, so it also likes 2 bonds or 2 lone pairs, but sulfur has kind of an additional option like what we see here. Sulfur can also do 4 bonds and 1 lone pair to give it a 0 formal charge. Oxygen can't do that because that gives it 10 electrons and oxygen can't expand its octet. Oxygen doesn't have d orbitals that are accessible to kind of put any of those extra electrons into. It's not far enough down the periodic table. The other side of that, besides just d orbitals, is also just size. Like the second row elements and kind of those first elements are almost kind of too small to have that many electrons around them. The repulsions become kind of a problem also. Third row, not only do we have the d orbitals, they're also just big enough to kind of spread those electrons better. And so it's easier for those elements to do that and take those expanded octets. But I do want to take a look at, let's draw a Lewis structure for sulfate. So SO4 2 minus. And this will be, I think, a good example of when expanded octets and formal charges kind of come together. And I think it's kind of maybe the last, maybe I guess, caveat or kind of like thing we have to pay attention to with these structures at the end to just look out for. So going through kind of our normal steps, if I'm counting my valence electrons, sulfur, like the last example, has 6. Oxygen also has 6. We have 4 of them. And if I have a -2 charge, that means I'm adding 2 electrons at the end to that total. Right. So in this case, I should have 32 electrons total. Skeletal structure wise, I'll have a starting sulfur in the middle. All my oxygens attached to it. Just single bonds to start. Now I can go, once I have the skeletal structure, fill all the outer octets. So that's 3 lone pairs on all of those outer atoms to give them octets. And if I had 32 electrons initially, if I have 4 octets, 4 times 8 is also 32. So I don't have anything left over to put on sulfur. And if I'm looking, sulfur has an octet, right? It's got 8 electrons around it because of those 4 bonds. And so I think a lot of times people are like, oh, sulfur has an octet, we're done. That's the best structure that we can have. The problem here is if I look at formal charge, and this is why I kind of always say, check for formal charge, and also kind of check for resonance if there are multiple bonds. Because if I look at all my formal charges here, what do I notice about all those outer oxygens? We said a second ago, oxygen likes 2 bonds and 2 lone pairs is what gives it 0 formal charge. All of these have 1 bond and 3 lone pairs, which means if I'm kind of doing the calculation, like each of those oxygens, 6 valence electrons, minus 6 electrons in lone pairs, minus a bond. Every one of these oxygens has a negative formal charge right now. And if my whole thing only has a -2 charge and I have 4 negative charges like that, what's the formal charge in that sulfur then? Yeah, it's got to be +2 at the moment. And I can do that quick if I just do the math, right? 6 valence electrons minus none in lone pairs minus 4 bonds. That'd be a +2. And formal charges like +2 and -2, for the most part, are really bad. They're really uncommon. If there's any way to get rid of a +2 or a -2 formal charge, like pretty much that atom or that molecule is always going to try to do that. So how that can happen, how we can get rid of some of the formal charge in this case, is by making multiple bonds. So for instance, if I look at that, say, top oxygen, and let's say I take off this lone pair and make a second bond, now all of a sudden that top oxygen has 0 formal charge. And in addition, my sulfur now would be 6 minus 0 minus 5, which is only a +1 formal charge. So I've at least made the formal charge better, but I can still get rid of more formal charges if I make a second multiple bond, right? So for instance, if I were to say, take 2 electrons off the right oxygen and make a double bond there. Now all of a sudden, 2 of those oxygens have gotten rid of their formal charge, right? They have the 2 bonds and 2 lone pairs they normally like. Sulfur now would be 6 minus 0 minus 6, which is also a 0 formal charge. Now, it does have 12 electrons on that sulfur, but again, As long as that atom's third row or lower, more than 8 electrons is okay. It can do that. And it turns out this is actually a better Lewis structure, but there's one other thing I have to consider. How did I know I'm putting those double bonds on the upper and the right oxygen? Kind of don't. They could have gone to the other spots too. This means this thing does have resonance. Right, so really those 2 double bonds, they could be drawn like this instead, or they could be drawn as, and really this one has a lot of different resonance structures. And for something like sulfate, I would probably not make you draw all of them because there's a lot of combinations of where exactly those two could be. But some indication that there is resonance going on, something that I would look for. So the important thing is this does have resonance. And really what that means in this case, if I'm looking at it, if this is kind of my structure for just one of them, it's got kind of this overall 2- charge. I have 2 double bonds that can be spread across kind of 4 spots. So kind of on average, almost each one of those bonds is getting like an extra half of a bond. So really every one of those sulfur oxygen bonds isn't a single bond or a double bond. It's really more like a bond and a half each because they are all evenly kind of being distributed. Now, one other notation way that we'll sometimes see this shown, things that have resonance, when you have to draw Lewis structures, I'm never going to want people to draw them this way. But reference-wise, if you're looking at like a textbook or something like that, you will sometimes see things that have resonance drawn like this, where they have dashed lines for the second bond. That's another version of notation for resonance. If you see dashed lines like that, it means all of the bonds that have that dash have some kind of resonance that's present. It basically means they're more than a single bond, but they're less than a double bond because you have kind of extra electrons being shared between those different bonds. I do not usually want people drawing things this way, but I do just want to highlight that if you see that, those dash lines that way do indicate resonance. What's probably more useful to us is seeing a structure like this, knowing that we do have resonance. Like I said, for sulfate, I probably wouldn't expect you to draw all of them because there's like 6 resonance forms. Most things usually only have like 2 or 3 at the most. But takeaways as far as what that means, if I have 2 double bonds being shared across 4 spots, really like each sulfur oxygen bond is kind of like a bond and a half. Is probably kind of the thing we want to be able to recognize from that. And on that note, how we know all of those are kind of even in terms of their like relative bond strength, I do want to mention one quick trend as far as how bond length and bond strength are correlated to each other. Stronger bonds are always going to be shorter. The atoms are going to get pulled closer together. And when I say stronger bonds in this case, I'm really talking about like single bond versus double bond versus triple bond. Like a triple bond is stronger than a double bond is stronger than a single bond. But as your bonds get stronger, the bond lengths get shorter. It's kind of the general trend. So stronger bonds lead to shorter bond lengths. So for instance, like a carbon-carbon triple bond is shorter than a carbon-carbon double bond, and a carbon-carbon double bond is shorter than a carbon-carbon single bond. And if you go on to take organic chemistry, you'll see a whole bunch of variations of carbon doing like single bonds, double bonds, triple bonds for a variety of different compounds. All right, so all of this is kind of a lot of just introductory information to drawing these Lewis structures, but I do want to just go through just a handful of examples, just going through the steps, hopefully seeing that really it is just the same exact systematic steps every time. Just kind of being careful at the very end, just check for formal charge or resonance and kind of if those things are there. All right, so to do some examples, let's take a look at, let's do IF4 plus. So going through just normal steps or patterns, iodine being our first element here, finding total valence electrons. Iodine's a halogen, it's down under fluorine. So it's going to have 7 valence electrons. Fluorine also has 7 valence electrons. There are 4 of them. And if I have a positive charge, what is that doing to my total? Negative charge is added electrons to my total. But if I have a positive charge, that means I've taken an electron off, right? So I actually need to -1 from that total because of that positive charge, right? So in this case, that's going to give us a total of 34 electrons. So if I'm going to go through my steps, iodine's listed first. So that should be our central atom. 4 fluorines. I can fill all of my outer octets. So 6 electrons on each of them. And how many electrons is that going to use to that point? That should be 32. If I started with 34, that means I have 2 electrons left. So what happens to those? Anytime I have leftover electrons, they're always going to be a lone pair on the central atom. They'll never do anything different. So lone pair on the iodine. All right. Once I've added all the electrons that I have, I check, does my central atom have an octet? Well, in this case, how many electrons does that iodine have? It has not 8, but I got 4 bonds plus a lone pair. That's 10 electrons, right? So iodine has 10 electrons. Is that okay? Well, if I look where iodine is on the periodic table, it's way down in like the 5th row. So it just has to be in the 3rd row or lower. So that's fine. So iodine having 10 electrons, that's okay. So don't have anything as far as like octet rule stuff I need to change. Formal charge. If I have an overall positive charge on this whole thing, which usually, again, overall charge means like I'm going to put all this in brackets with positive charge. But if this whole thing has a positive charge, that means I have to have a positive formal charge somewhere in here. Where is the positive formal charge? Can it be on any of the outer fluorines? If all the outer fluorines look exactly the same, really can't be on them. That means the positive formal charge has to be on the iodine. And again, we can go through kind of the calculation steps for formal charge. Like for the iodine, 7 valence electrons. It's got 2 electrons in lone pairs. It's making 4 bonds. It's +1 for that iodine. So that's what we see on the formal charge. So that would be then our full Lewis structure for IF4+. Questions going through kind of any of the steps? Doing this part for that, or why we added these. So we added those because we had 34 electrons to start with. And once we'd filled all the outer octets, we looked at how many total electrons we'd added to the whole structure at that point. And at that point, we'd use 32. And so, yeah, so we're seeing what's left. And so anytime there's electrons left, that's why we kind of count them at the start. Anytime you've added all the outer electrons and you have electrons left over still, they will always be lone pairs in the central atom. And that will always be the case for that. Right. Any other questions on this one going through kind of our steps? All right, let's take a look at CO2. So a little bit smaller elements involved this time. So CO2, just kind of doing our normal steps. Carbon has how many valence electrons? Based on where it is in the periodic table, should be 4, right? Oxygen's got 6, we got 2 of them. So total, this should be 16 electrons. So oxygen has 16, or sorry, the CO2 has 16 electrons. Central atom, it's going to be the first one listed. So carbon. So carbon's our first element. Just out of habit, I usually draw it side to side. So carbon with 2 oxygens. I'm going to start by filling my outer electrons. But then when I get to this point, how many electrons have I used? Well, counting all of those, if I have 2 octets, 2 times 8 is 16, right? So if I started with 16, used all 16, I don't have anything left to put on that carbon. So no lone pairs in the carbon. Am I done? What's still wrong with the structure? What has to happen to that carbon? Yeah, it needs an octet, but it's only right now, it's only got 4 electrons, right? So that means it's going to need multiple bonds. It's actually going to need more than one. So I can make a multiple bond by taking a lone pair off one of the oxygens, making a double bond. Right? That gets my carbon to 6 electrons. Now I actually have an option because I still need 2 more electrons on that carbon, but I can do that by either taking a lone pair off of the other oxygen to make 2 double bonds, or my other option is I could have had a triple bond to the left oxygen and just left the single bond on the other side. Which of these is better and why? Because they're not equal. Technically, both of those, the way they're drawn, follow the octet rule, but one is better than the other. What's the other thing we usually check when we finish? We look at formal charge, right? So if we look at formal charge, what's the formal charge on the oxygens in the first one? Or both. If I do formal charge for each oxygen, 6 valence electrons minus 4 electrons in lone pairs minus 2 bonds is 0. That'd be the case for both of them. What about the bottom one? Like if I'm looking at this oxygen, 6 valence electrons minus 2 electrons in lone pairs minus 3 bonds is +1. Where the other oxygen is 6 minus 6 electrons in lone pairs minus 1 bond is -1. So I'd have like a +1 and a -1. But what did we say about formal charge? What do we prefer? We always want to have as many 0 formal charges as possible is kind of the goal. So if everything is a 0 formal charge in this top version, that's the better structure. Right? So CO2 is going to have 2 double bonds to those oxygens, not a double or not as a single and a triple. So use formal charge to help, like if you have like options like this, and you're not sure, like, well, they're definitely not equal. They don't look exactly the same. Like you can use formal charge to help kind of differentiate which of those 2 structures should be the better one. And probably as a quick rule of thumb, if the outer elements are the same, symmetry is probably going to be favored. Like that's probably going to be the usual outcome. If the outer elements are different, that's when maybe you'll get something different. So to kind of compare that, let's say we had I'm going to do CSF. Actually, no, I don't want sulfur. Let me do phosphorus. All right, which is a pretty weird looking formula. It's got 3 elements in it. Carbon's still first, which means I am going to put it as the central element in this case. But if I'm going through my normal pattern, I'll have 4 electrons on carbon. Phosphorus is under nitrogen, so it's going to have 5. Fluorine has 7, so we have 16 electrons total, kind of just like the CO2 example. Carbon, if I pick as the central atom again, since it's first, connect the phosphorus and the fluorine to it. I can fill my outer octets. Should be looking fairly similar to CO2, at least at this point, right? Because filling all those outer octets is again going to use all 16 electrons. So I don't have anything left to put on that carbon. In this case, though, if I'm going through my steps to get that carbon and octet, I need to make multiple bonds, but which atom am I going to make multiple bonds to? And we can kind of check this a little bit with like formal charge, again, things like that. But the way this is going to end up better is if I make the multiple bonds to the phosphorus in both cases, as opposed to doing, say, 2 double bonds like we did before. So here, if I'm looking at formal charge, for the top one that has the triple bond and the single bond, phosphorus, right, 5 valence electrons normally, 2 electrons in lone pairs, 3 bonds is 0. Right, fluorine, 7 valence electrons normally, 6 electrons in lone pairs, 1 bond, 0. So that top version right now has all 0 formal charge. The bottom one, if I try to do the 2 double bonds, phosphorus here would be 5 minus 4 electrons in lone pairs minus 2 bonds is -1. So this phosphorus would have a -1 formal charge. And the fluorine, 7 minus 4 electrons in lone pairs minus 2 is +1. So if we have a positive formal charge, well, if the top one has 0 formal charge, that means that's the better one in this particular case. So use formal charge if you have kind of options of where to make multiple bonds to try and figure out which one is better. If both your outer atoms are the same, probably some kind of symmetry is probably going to be what's going to be preferred. But if the outer elements are different, probably one of them is going to prefer having like extra or different multiple bonds. So check your formal charge kind of for those to help a little bit, I think. One other thing I'll kind of point out, if you do have formal charges in your compound, the more electronegative atoms usually like to have the negative formal charge. So like in that bottom version, fluorine has a positive formal charge, but fluorine's the most electronegative element. So fluorine is pretty much never going to have a structure that has a positive formal charge, pretty much ever. And so you can use that to kind of help to predict where things might go. Like if you have to have formal charge, negative formal charges usually like the more electronegative elements, which are often the outer elements. Your central atom is often more likely to have a positive formal charge in a lot of structures because it's usually the least electronegative of your elements. Questions looking at those two comparing? Let's do some more polyatomics. Let's take a look at carbonate, CO3 2 minus. So going through normal steps, carbon, 4 valence electrons. Each oxygen has 6. We have 3 of them. And a -2 charge means that we're adding 2 more electrons to that as well. So our total number of electrons here, 24. So as I go to put my structure together, carbon is first. 3 oxygens attached to it, filling all of the outer octets. Same steps as always. Gets me to this point. From here, if I want to look at what I have left, how many electrons have I put into that structure? I have 3 octets, 3 times 8's 24, started with 24. So don't have anything left. Right? So no lone pair in the carbon, but is this my final structure? Yeah, what do I still need to do? Carbon still wants an octet, but it only has 6 electrons. So how do I get it to an octet? Yeah, I need to make a double bond. Where am I making it? It doesn't matter. Yeah, it really doesn't, because this is, again, going back to this is resonance, right? Because I can put the double bond to this top oxygen, right, by getting rid of one of its lone pairs. But in reality, I could have put that double bond to any of the other oxygens also, right? There's no difference between which element I made that double bond to. Now I'm going to put all this in brackets because it's got an overall 2 minus charge. And if I wanted to show resonance, usually the way I'll do that, I'll just show the double bond kind of moving around. It could have been in the bottom left or the bottom right, the way that we drew it. So the double, just kind of showing the double bond can move. And the one last piece that I do have to add to this, still on kind of the right part of this, is to probably put the formal charges in. If I have a -2 overall charge, that means I have to have negative formal charges somewhere in here. Where are my negative formal charges? This is something that the more of these you do, you start to see patterns. Oxygen likes 2 bonds and 2 lone pairs. So whenever oxygen makes just 1 bond and has 3 lone pairs, that's always a negative formal charge. So both of these bottom oxygens have negative formal charges on them. That would be then kind of our full structure with kind of the shorthand kind of notation for the resonance. Questions on how we got to that, where the resonance is coming from? Right, if we do, let's do one that's a little more mixed. Let's do let's do the question first.
So, like it's like CO3 2 minus, so would that be the overall charge at the end?
Yes. So yeah, like when you have like the 2 minus charge, like on the whole thing, if you add up all the formal charges, they have to add up to that total. Yeah, and that should always happen. And that's why like things that are neutral, like overall, ideally we want all 0 formal charges because there shouldn't need to be any, hopefully. Or maybe a couple tiny exceptions. There has to be, like ozone is one, for example. But usually if it's a neutral molecule, probably you can have all 0 formal charges. But if you have a charge, there has to be formal charges somewhere that add up to that charge. All right, let's take a look at, and actually if I'm writing this in the right order of elements, it's probably going to be like this. CSCl2. So I want to draw a Lewis structure for this compound. So here, just again, normal steps, carbon, 4 valence electrons, sulfur has 6, it's below oxygen. Each chlorine is going to have 7 because it's below fluorine on the periodic table. So adding all these together, should have a total of 22 electrons. If I go to kind of put things together, I'll have central atom, first one listed, right, going to be carbon. Again, if the first element listed is not the central atom, we'll probably give you something to help identify that. So carbon central, we connect sulfur, 2 chlorines. Fill all the outer octets. Oh, actually, did I do something wrong in my? Yeah, I can't do math. It should be 24 total. So I get to this point. I filled all my octets. How many electrons is that? Kind of similar to the last example. Right, it's 24. So if I've used all 24 electrons, I don't have anything left to put on the carbon. But my carbon at the moment, like the last example, has just 6 electrons still. So I need a multiple bond. Where is the multiple bond going to go? Yeah, it is going to go to the sulfur. Why the sulfur and not the chlorine? Yeah, it's going to be formal charge, kind of helps predict that, right? Sulfur is below oxygen, which means sulfur usually will want probably like 2 bonds and 2 lone pairs. Particularly if it's an outer atom, sulfur will usually do 2 bonds, 2 lone pairs. So in this case, taking the lone pair off of the sulfur to make the extra bond, that's what's going to give sulfur 0 formal charge and carbon the octet. If I'd have made the double bond to a chlorine, one of the chlorines would have got a positive formal charge, which we don't want. And so at the end of this, by making the double bond with the sulfur, all my formal charges here are going to be 0. And there is no resonance this time, right? Because that double bond isn't going to go to the chlorines. It's not equal, right? If the double bond went to the chlorines that have formal charges that are not 0, it's just a worse structure at that point. So for things to be equal and have resonance, kind of formal charges have to be kind of the same. Like there's no preference on formal charge. That's what kind of creates the resonance effect. Questions on this one kind of going through? Take a look at maybe one more, and I'll talk about kind of one thing we'll add to this and take a look at next time too. So let's do something that has hydrogen. Let's do let's do this. This is something that's going to pop up plenty in 1212 as well. All right, so H3O plus. This is called the hydronium cation or hydronium ion. So going through normal steps, hydrogen only has 1 electron each. Oxygen has 6. If I have a positive charge, though, that means I'm taking an electron off. Right, so total electrons here, I only have 8 electrons, but I still am just following my normal steps. Right, oxygen is going to be my central atom. And well, for that part, oxygen I'm putting central. Usually it's the first element, but remember hydrogen can't be the central atom. So oxygen coming second. Oxygen is going to be the central element this time. 3 hydrogens attached to it. How many electrons does that, and really, do I need to put octets on hydrogens? No, remember they're just going to make the bond. How many electrons will it take to get to that point now? Yeah, just 6 for the 3 bonds. I started with 8. Right, that means if I have 2 electrons left, that oxygen does have 1 lone pair. That does give the oxygen an octet. But if this whole thing has a positive charge, I do still have to have a positive formal charge somewhere too. So where's the positive formal charge? Oxygen normally likes 2 bonds, 2 lone pairs, but here it's got 3 bonds and 1 lone pair. So it's the oxygen that has the positive formal charge this time. And so this just shows, like, for hydrogen in particular, like, hydrogen always an outer atom, doesn't need an octet. It's just going to have the bond like that. Kind of the one variation that we kind of throw into some of these things. All right. Questions having run through any of these examples? I think between kind of seeing this, and like I said, if you haven't been to lab yet this week, you'll see it more there too. Thursday, we'll get more into kind of the VSEPR and the shape side. The last thing I want to talk about today is actually one thing relating back to energy stuff that we actually saw earlier this semester. And that's that we can calculate the change in delta H for a reaction, or change in enthalpy of a reaction, using bond energies. We didn't do this earlier because without Lewis structures, we really couldn't do this properly. We needed to kind of have Lewis structures, or know how to draw Lewis structures to be able to do this. So how this works is this is usually going to be our delta H of reaction. Before we had enthalpies of formation, it's like products minus reactants. In this case, it's really bonds broken minus bonds formed, which, if you're thinking about it, your bonds broken are going to be the bonds that are in your reactants. So it's kind of the reactants minus the products in this case, which may seem a little backwards, but it's because of the energy and kind of like what's happening, right? If we're breaking bonds, we're putting energy in to break bonds. When energies form, they release energy. And normally when we see bond energies or tables of bond energies, they're always listed as positive values. It's the energy it takes to break the bonds. So that's why this looks like this for this order. How this works, I think it's easiest to show with an example. So let's take a look at the last ones here for the day. So this wants us to calculate the enthalpy change for this reaction, given the table of bond energies here. And so we have 2H2 plus O2 going to 2H2O, and we're given these different bond energies. And so it is, like I said before, it's the bonds broken minus the bonds formed. But the bonds that we're breaking, the way we have to kind of do this is we look at the reactant side, and we basically need to draw the Lewis structures of those things. And we need to look at what bonds are actually breaking and how many of them there are. So for me, the way that I would normally do this, swap that quick, is that I'm going to draw out the Lewis structure of each of these compounds, and I'm just going to draw how many of them there are based on kind of the coefficients. So if my reaction was 2H2 plus O2 going to 2H2O, what I'm going to do is I'm basically going to draw a Lewis structure of H2, which is really just a hydrogen single bound to itself. That's it. There's only 2 electrons for H2, so that's just the one bond, right? But if I have 2 of them, I'm going to draw it twice just to kind of keep track of how many bonds there are. But for O2, if I draw my Lewis structure, and this is the part that's kind of important, O2 is actually going to have a double bond. If I go through my normal steps, right? And I can do just the normal steps real quick just to show everyone kind of where it's all coming from. O2 should have 12 total electrons. And connect them, fill 1 octet, right? That takes up 8 electrons. If I started with 12, I'll have 4 more, so that's 2 lone pairs in the other oxygen. But one of those oxygens doesn't have an octet yet, so I'll end up with a double bond, so that I have an octet on each. And again, kind of normal patterns. Oxygen likes 2 bonds, 2 lone pairs. Both oxygens do that. And then on the product side, I'm making 2 waters. Lewis structure for water, if I was going through things, hydrogen can't be central, oxygen is. So each water has an oxygen with 2 hydrogens on it. Hydrogen can only make that single bond. If I'm looking at total number of electrons, like H2O, each hydrogen is 1, oxygen 6, that's 8 total. So in my structure, if I have 2 bonds to hydrogens, it's 4 electrons, so 4 left for lone pairs. But if I have 2 of these, and what I'm looking at is really kind of my total number of bonds, right? So on my reactant side, I have 2 hydrogen-hydrogen bonds and 1 oxygen-oxygen double bond. And the fact it's a double bond is important because the bond energy of an oxygen-oxygen double bond is different than a single bond, and it's not equal to 2 times a single bond energy either. And that's the real important, I think, difference there. We'll see that in the chart that I'll show in kind of a second. So these are our bonds kind of broken, right, versus formed on the product side. And over here, if I'm looking, I'm forming 4 oxygen-hydrogen bonds total. Right? I have 2 oxygen-hydrogen bonds in each water. And so really in terms of setting up my calculation, I should have all my bonds that are being broken. So the 2 hydrogen-hydrogen bonds, the 1 oxygen-oxygen double, and then I have my bonds being formed, which is just the 4 oxygen-hydrogen bonds. So putting in kind of numbers to this, my delta H for this reaction, I just want to go through and look then for hydrogen-hydrogen in the chart. My hydrogen-hydrogen bond energy is 432. So if I have 2 of them, it'll be 2 times 432 kilojoules per mole. Plus, if I have 1 oxygen-oxygen double bond, and this is where the double bond part's important. If I'm looking at this chart, I want to find the oxygen-oxygen double bond, which you'll notice is a lot more than the oxygen single bond just being doubled. They're not the same. So oxygen-oxygen double bond down here at the bottom, 494. I have 1 of them, so 1 times 494. There's all my bonds being broken. And then I want to subtract all my ones that are being formed, which is just 4 oxygen-hydrogen bonds. So in this chart, I want to find oxygen and hydrogen. Its bond energy is 459. I have 4 of them, so 4 times 459 kilojoules per mole. And now I'm just going to calculate what that number comes out to. So if I'm punching the numbers on this, 2 times 432 plus 1 times 494 minus 4 times 459. And it looks like it's negative 478 kilojoules per mole. That is now my delta H for that reaction. So this just gives us kind of a different perspective on how we can calculate delta H using bond energies. But we needed to be able to draw kind of Lewis structures to do this, so we hadn't done it yet. So Thursday when we come back, we'll look at doing maybe 1 or 2 more quick examples of this. Then we'll get into kind of the VSEPR and kind of 3-dimensional shapes that these molecules have as well. Next application.